All right, so now we're moving on to type 3, which is our last weak acid calculation. And then after this, we switch to weak base. And my thought was probably in class, we'll get to the end of weak acid, and then the weak base will be kind of a nice recap of everything we did with weak acids in weak bases. So the last type of weak acid calculation is going to be to find the initial concentration or mass of an acid, okay, of this weak acid. So what they're going to give you is they're going to give you pH, they're going to give you Ka, and your job is going to be to find the initial concentration of the mass. And so of course we're going to use Rice tables. So the question will say something like, what mass of ammonium chloride will produce 1.5 liters of a solution with a pH of 4.75? Now the first thing you have to be aware of is that if you have ammonium acting as your weak acid, you're never going to have ammonium ions that you can take the mass of. It's going to be in the form of a salt. So your salt, this ammonium chloride, dissociates to ammonium ions and chloride ions, and it's the ammonium that's going to act as your weak acid. So everything that we are going to do is going to be with this acid, and the chloride ion is just going to be a spectator. So when they give us pH of 4.75, this is going to be the same as our type 2. We're going to find the concentration of hydronium or hydrogen at equilibrium by doing 10 to the negative 4.75. Okay, now I've learned my lesson that I like putting this into my calculator. So 10 to the negative 4.75 will give me a hydrogen ion concentration at equilibrium of 2 decimal places in my pH, so 2 sig figs, 1.7 dot 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 times 10 to the negative 5 molar. So then let's fill out our Rice table. So whoops. What have I done? Vertically. RICE. There we go. This happens when I try to do too many videos in a day. I'm starting to go loopy. Okay, somebody who is very A-type is going to hate that line I just draw. Okay, let's try to make it a little more straight. There we go. Okay, so we have NH4 acting as our weak acid, and it's going to produce a hydrogen ion and a weak base, or a conjugate base. So maybe you could write yourself, if it helps, right? NH4 as a weak acid is in equilibrium with a hydrogen ion and ammonium. So ammonium would be your conjugate base. So hydrogen ion and ammonium. Okay. So now we know that the hydrogen ion concentration at equilibrium is that 1.7 dot 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 times 10 to the negative 5. And we know that we would have started with nothing and some concentration of ammonia initially. But the hydrogen went up by X, and so did the ammonium by the same ratio. So the concentration of ammonium will also be the 1.7 times 10 to the negative 5. Now, the concentration of I think I used the wrong word. This is ammonia. This is ammonium. The concentration of ammonium at equilibrium is going to be minus X. So it's going to be the concentration of ammonium initially. So the concentration of ammonium at equilibrium is going to equal the concentration of ammonium initially minus X. Just like these questions we did in other units, you kind of get a choice of which way you want to set up our calculation. This is where we're going to use Ka. Now, this is a known acid. This is ammonium. We can look in our information booklet and look up for the Ka value of ammonium, which is down here, and it is 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10. So then what we're going to do is we're going to set up our Ka expression. So Ka is equal to the concentration of hydrogen at equilibrium times the concentration of that conjugate base, ammonia, divided by the concentration of ammonium at equilibrium as well. So now in for Ka, we're going to put 5.6 times 10 to the negative 10. In for the hydrogen ion concentration at equilibrium, we're going to put that 1.7 times 10 to the negative 5. And then you're timesing that by itself. So I'm going to put squared, right? The concentration of ammonia and hydrogen is the same. And then you kind of get two choices at this point. Some people, and you should know who you are at this point because we've been doing this in other calculations as well, you can keep the math simple in here. And you could say, okay, I'm going to find the concentration of the ammonium at equilibrium. Or if you like to do things in one step, you can put in the Ka as 5.6 times 10 to the negative 10. You could put in the concentrations as 1.7 times 10 to the negative 5 squared. But instead of putting ammonium at equilibrium, you could put that the concentration of ammonium sorry, I just had a brain fart for a second. The concentration of ammonium at equilibrium is equal to the concentration of ammonium initially minus that x value, which is that 1.7 times 10 to the negative 5, right? So it's not that big of a difference. It's whether you want to find the concentration at equilibrium and then put that in to find the concentration initially, or whether you want your calculation to do it all in one step. Totally up to you. So for me, what I'm going to plug in, I'll do both. I'm going to make sure, I actually had a small mistake in my video, so I had to redo it. I put times 10 to the negative 3 instead of times 10 to the negative 10. So I'm just going to plug in my concentration again. So 10 to the negative 4.75. Okay, so I'm going to hit that as store A. All right. So I'm going to plug into my calculator to find the concentration of ammonium at equilibrium. You're going to do that 1.7 times 10 to the negative 5, and I have that as stored as A, or you have to write down a lot of decimal places, divided by the 5.6 times 10 to the negative 10. So I'm going to hit into my calculator, I'm going to hit recall A, and I'm going to square it, divided by 5.6 times 10 to the negative 10. Which gives me we're going to go to 2 sig figs, so 0.56 ... because I'm going to have to use this again, moles per liter. Then if I wanted to find the concentration of ammonium initially, you're going to take that concentration of ammonium at equilibrium and you're going to add X back on, right? So if you think about this, if we're at equilibrium and we want to go to initial minus X is equilibrium, equilibrium plus X is initial. So we're going to add on that X value. Now the funny thing that's going to happen is you've got that 0.56 and then you're adding, times 10 to the, and so then you're adding on to that value of 1.7 times 10 to the negative 5. Now, this is where we talk about negligible. Watch what happens when you plug this into your calculator. So I've got 0.56 plus that recall A, and it still gives me 0.56. Nothing's going to change because this amount that it decreased by is so negligible that it stays the same. Now, if you were plugging this one into your calculator, right, you would take that concentration of ammonium initially minus the 1.7 times 10 to the negative 5, and it's the same work, right? 1.7 ... times 10 to the negative 5 squared divided by 5.6 times 10 to the negative 10 is going to give you an answer, and then you're going to add that 1.7 on. So it's the exact same work, it's just whether you want to do it all in one step or whether you want to, get that equilibrium concentration and then do one more step past there. So I would go recall A squared divided by 5.6 times 10 to the negative 10, and then I would add recall A. And that still gives me that 0.56. I'd say the downside of that is that you didn't see that negligible piece, which I thought was really kind of cool. But, kicker, this isn't what they wanted. They didn't want the initial concentration of ammonium. They wanted the initial mass of ammonium chloride. Whew. So we now know the concentration of ammonium at equilibrium, and we want to know the mass of ammonium chloride. So this is going to be in a 1-to-1 ratio. So if the concentration of ammonium is that 0.56 moles per liter, then the concentration of ammonium chloride is also that 0.56. So good old dimensional analysis. We've got that 0.56 moles per liter of ammonium chloride. And we want to find the mass of ammonium chloride that you would add. So we know that 1 mole of ammonium chloride, don't use ammonium, it would be what? So I'm going to store that. Okay, so nitrogen is 14.01, hydrogen, there's 4 of them, and 1.008, and then a chloride is 35.45, gives me a molar mass of 53.492 grams. And then the volume to get rid of liters was 1.5 liters. So I'm going to take that 53.492, times it by my recall A, or my 0.56 ... and then times that by 1.5. And I get to 2 sig figs 45 grams of the ammonium chloride was originally added into the solution. Holy, that's a lot. Hope you're feeling okay.